Imagine you're trying to assemble, like, a piece of flat pack furniture.
Oh, the worst.
Right. You open up the manual, and you're hoping for a nice, easy step 1, step 2. But instead, the very first page just shows you the completely finished, fully assembled bookshelf.
Wow. Okay, so no actual steps.
Exactly. So to understand how to actually build it, you have to read the manual from the last page to the first page. You're basically decoding the steps in reverse order.
That sounds like a nightmare.
It is. You're starting at the end result and mentally working backwards just to figure out, which screw goes into which board.
And the cognitive friction of that, of trying to reverse engineer a process while you're simultaneously just trying to, like, hold a heavy piece of wood in place, it's intense.
Right.
Your brain is doing double duty. You are translating the instructions backwards while trying to execute them forwards.
Yeah, and that exact tension between how a system efficiently operates and how a human mind actually wants to process information that's at the heart of today's deep dive. Welcome, by the way.
Glad to be here.
So we're looking at a fascinating teardown published today, July 22, 2026. It's by a developer named Ang, and it's titled Notes-on-Haskell-Programming Part 193, Refactoring for Readable Haskell Codes.
Which I know sounds super technical, but we're essentially taking a microscope to just a few lines of Haskell code.
Just a tiny piece of refactoring.
Right, because the themes Ang wrestles with here, they apply to systems architecture, to design, and honestly, even how you structure an argument.
Yeah, it's really about that eternal tug of war, right? Between optimizing a system so it's flawlessly elegant for a machine to process versus making it intuitive and, frictionless for a human being to read.
Exactly. So Ang sets the stage with a scenario you've probably encountered if you've ever dealt with data exports.
Oh, yeah. So there is this data type in the code called export format. And if you imagine, like, a program dealing with sections of a translated Chinese novel, you need to export those sections into various file types.
Yeah, the standard ones.
Yeah, formats like PDF, TEEP, EPUB, TXT, and DUMI. And in the code, the first letter of each is capitalized.
Right, because in Haskell, those capitalist terms are the data constructors. But the operating system doesn't want a capitalized constructor when it creates a file.
No, it definitely doesn't.
It wants a standard lowercase file extension, like .pdf in all lowercase. So the system needs a translation layer.
Right. So Ang originally had a function called extension to handle this exact translation. And the original state of this code is what developers universally call boilerplate.
Oh, the dreaded boilerplate.
Yeah, it was just purely manual mapping. The code literally read extension capital PDF equals, quote, PDF, unquote, in lowercase.
Very literal.
And then the next line down, extension tip equals tip. Next line, extension EPUB equals EPUB, and so on, for every single format they had.
I mean, brute force pattern matching like that is incredibly common in early stage code bases.
Oh, totally.
And on one hand, it is incredibly easy for the human eye to parse. You look at it and you instantly know what it does, but structurally, it is a huge liability.
Yeah, it reminds me of running a diner.
Okay, how so?
Let's say you decide to start serving tomato soup. You don't just, type tomato soup into a single centralized database that magically updates everything.
Right, you have to do it everywhere.
Exactly. You have to walk over and write it on the physical kitchen display board. Then you log into the cash register system and manually program a new button. Then you have to call the web developer to update the HTML menu on the website.
Which is exhausting just to think about.
It is. You are duplicating the concept of tomato soup across multiple distinct manual systems.
And the maintenance burden is the real threat there. Anga points out this exact vulnerability. Because if a developer later decides to add, say, an HTML export option, they have to remember to update the code in two entirely separate locations.
Oh, right.
They have to add the new constructor to the export format data type at the top of the file, and then they have to scroll all the way down and add a brand new manual translation line to that extension function.
And you just know someone's going to update the data type, get pinged on Slack, get completely distracted, and forget to add that second translation line.
Exactly. I mean, the compiler might catch it if you have the right warnings enabled, but if not, the program hits a format it doesn't recognize and it simply crashes.
That is the worst case scenario.
Right. Because the machine doesn't care about the repetition. It will happily execute 1,000 manual lines of pattern matching in microseconds. But for you, the human maintaining the system, it's a trap.
Yeah, every manual duplication is basically a point of potential failure.
Exactly. And the drive to refactor is usually born from a desire to eliminate that exact vulnerability. You want a centralized system that dynamically handles any new input without requiring a human to manually wire the connections every single time.
So Ang decides to tear down those manual whiteboards, essentially.
Right.
The first major refactor deletes all those repetitive lines and replaces them with a single, highly condensed line of code. Looks like this. Extension equals map to lower.show.
Okay, so to understand the mechanics here, we need to quickly look at what those two functions do.
Let's break it down.
So show is a built-in Haskell function. It takes a data constructor, like that capitalized PDF, and turns it into a string representation. It essentially just puts quotes around it.
Okay, so the capitalized PDF becomes the string PDF.
Yes. And because a string in Haskell is actually just a list of characters, Ang uses map to lower. The map function traverses that list of characters, applying the to-lower function, which is from the data.char library, to each individual letter. So capital P becomes lowercase p.
Got it. But the really fascinating part to me is how these two operations are glued together.
The dot.
Yes, they're connected by a single dot, a period.
Yeah.
And notice what is completely missing from that line of code. There is no explicit variable.
Right. It doesn't say extension format equals. It just says extension equals.
Yeah.
Functional programmers refer to this as the point-free style.
Point-free.
Right, because the points are the variables, the specific pieces of data. By completely omitting the variable, the code elevates itself from manipulating specific data to defining a pure pipeline of logic.
Which, mathematically, is beautiful.
It is. You are essentially declaring, I do not care what specific format you hand me. My entire function is just the abstract concept of stringifying something and then lowercasing it.
And practically, if you add 50 new export formats to your data type tomorrow, you never have to touch this function again. It automatically handles all of them.
Total automation.
But I have to challenge the idea that this is the ideal solution.
Okay, let's hear it.
I'm looking at that dot operator, and I'm thinking about how our brains actually parse information. This function executes right to left, doesn't it?
It does. The dot represents mathematical function composition.
Right.
If you remember high school algebra, composing two functions, f and g is written as f of g of x. You always evaluate the inner function, g, first. Then you pass that result outward to f.
Oh.
So yes, the compiler reads this from right to left. It takes the invisible input on the far right, applies show, and then feeds that result to the left into map to lower.
See, I am really struggling to see how this is an improvement for the person actually reading the code. I mean, we naturally read text from left to right.
In English, yes.
Right. If you're scanning a file with hundreds of lines, this point-free style forces you to read backwards like Yoda. Lowercase, the string shall be.
That is a great way to put it.
You know, you start at the right, you figure out the first action, you hold that action in your working memory, and then you move your eyes to the left to see what happens next. It's that furniture manual problem all over again.
Well, I will defend the point-free style here for just a moment, because once you internalize the mathematical paradigm, that dot operator becomes incredibly powerful.
Okay.
You stop reading it as a chronological sequence of events, and you start reading it as a single holistic definition. You aren't seeing do this, then do that. You are seeing a mathematical truth. The extension is the composition of lowercasing and showing.
So it's about shifting your mindset.
Exactly. For a seasoned functional programmer, the lack of variables means less visual noise. The compiler loves it, and pure mathematicians love it because it eliminates state entirely.
Sure. But Ang isn't writing code for a pure mathematician in a vacuum.
No, they aren't.
Ang is writing code that has to be maintained by human beings who get tired. If you are staring at a pull request at 4:00 p.m. on a Friday, doing those mental gymnastics parsing right to left while holding state in your head, that is genuine cognitive friction.
And that is actually the turning point in Ang's post.
Oh, really?
Yeah, it's the realization that mathematical purity doesn't automatically translate to cognitive ergonomics.
Right.
We eradicated the maintenance burden of the boilerplate, yes, but the cost was intuitive readability. A machine doesn't care about the direction of the flow, but a human brain definitely does.
Yeah. So if the dot operator forces us to read backwards, Ang had to find a way to, flip the current. We need the machine to process the data left to right without reverting to that awful, fragile whiteboard method.
Which brings us to Ang's next iteration.
Okay, let's see it.
To fix the directional flow, Ang brings in a tool from the data.function library. It's the reverse application operator represented by an ampersand.
An ampersand. Okay,
yeah.
Let's look at the mechanics of this. So the code transforms into this. Extension FMT equals FMT ampersand show ampersand map to lower.
Right. And under the hood, the ampersand is incredibly simple, but really powerful. Its type signature essentially says it takes a value on its left side and a function on its right side, and it feeds that value directly into the function.
Wow.
It is literally reversing the standard application order.
See, this instantly makes more sense visually to me. It feels much more physical, like a factory assembly line.
I like that analogy.
Picture yourself standing in a facility. You take the raw material, which is the FMT variable here, you place it on the conveyor belt, which is the first ampersand.
Right.
It travels along the belt to the first machine, which is show. The show machine clamps down, turns the data into a string, and drops it back on the belt. Then it travels along the next ampersand, the next machine, mapped to lower, which stamps it into lowercase.
Yes, exactly.
You are literally watching the raw material get transformed step by step as your eyes naturally track from left to right.
And the visual structure of the code now perfectly mirrors the chronological execution of the logic. You don't have to hold operations in your head and work backwards.
Yeah.
It drastically reduces the cognitive load for anyone trying to understand what the data is actually doing.
But here, there's a clear casualty in this refactor.
Oh, the variable.
Yeah. If you look closely, we lost the elegance of the last version, and the explicit variable is back. We had to write extension FMT equals, and then start the assembly line with that specific FMT variable. We are no longer point-free.
No, we aren't. And this is where pragmatism overtakes mathematical purity. Ang deliberately sacrifices a bit of that functional elegance. Adding a 3-letter variable back into the code is basically the toll you pay to force the compiler to accept a left-to-right reading order using standard tools.
And it's a solid compromise, I think. But, programmers hate compromises.
They really do.
The ultimate goal here, the holy grail, would be keeping the absolute variable-dropping elegance of the point-free style, while simultaneously achieving that beautiful left-to-right assembly line readability. And Ang decides to go after that holy grail.
Right. And to achieve both goals simultaneously, the standard Haskell library is no longer enough.
Uh-oh.
Yeah. Ang has to turn to an external third-party package called the Flow library.
The flow library.
Okay.
And what does that do?
Well, it gives developers custom operators specifically designed to make data flow left to right without the cognitive friction. Ang outlines 2 final paths using this new tool.
All right, what's path 1?
The first path uses flow to achieve the point-free style. Ang uses an operator that consists of a dot followed by a greater than sign. Visually, it looks like a tiny arrow pointing to the right.
Oh, I see. So the code becomes extension equals show, dot greater than map to lower.
Right.
Look at how clean that is. The variable's gone again. It just takes whatever invisible input arrives, pushes it through show, follows the little arrow to the right, and pushes it through map to lower.
It is very slick, but then there's the alternative path. This uses flow to create a more explicit pipeline.
Okay.
It utilizes an operator made of a vertical bar followed by a greater than sign, which creates a much sturdier, distinct arrow shape.
Ah, okay. So for this one, the variable comes back. It reads, extension FMT equals FMT vertical bar greater than show vertical bar greater than map to lower.
Exactly.
It's identical to the ampersand approach, but visually much punchier. Those distinct arrows just draw the eye perfectly across the page.
They do, and both of these flow implementations achieve the goal. They align the visual syntax of the code with the mental model of the human reading it.
Hold on, though. I have to challenge the reality of this conclusion. We started with basic code. We refined it using built-in mathematical operators. Then we refined it again using built-in reverse application.
Right.
Now, to get this final, perfectly polished version, Ang is adding an entirely separate external library to the project's dependencies. Just to get a cute little arrow operator?
Well,
I mean, I have to ask if the juice is worth the squeeze here. Every time you add a dependency, you increase the bundle size. You introduce potential security vulnerabilities. You rely on code written by someone else that might just, stop being maintained.
it's true.
Doing all of that just so your code reads left to right seems like absolute overkill.
I hear you. And that pushback is totally valid if you are looking at a small personal script. But from an enterprise perspective, your argument ignores the single most expensive resource in software engineering.
Which is?
Developer time. Code is read exponentially more often than it is written.
That's a good point.
You might write that function once, but over the next 5 years, you, your teammates, and all the new hires are going to read that same exact line 100 times while tracking down bugs or adding features.
So you're arguing the cognitive ergonomics actually outweigh the dependency overhead.
Absolutely. When a developer opens a file, typing speed is never the bottleneck. Comprehension is the bottleneck.
Right.
If a team of 10 engineers has to pause for even a few seconds to mentally untangle a right-to-left dot operator every single time they scan a file, that friction compounds. The Flow library's visual syntax does the heavy lifting for the brain. It removes those micro-hesitations.
So it's an investment.
Exactly. In a professional environment, reducing the time it takes for a teammate to understand what you built is the ultimate goal of architecture. You gladly trade a tiny bit of dependency overhead to permanently lower the cognitive load on your team.
You're basically designing the system so the human eye slides over it with zero resistance.
You are optimizing the system for the human who has to live with it rather than the machine that just executes it.
Wow. Looking back at this evolution, it is a remarkable journey for a single tiny function.
It really is.
We started with the restaurant whiteboard. Just tedious manual mapping that was highly readable but completely fragile.
Right.
Then we swung completely to the other side. A mathematically pure automated pipeline that solved the fragility but, forced us to read backwards.
So the Yoda speak.
Right. Then we tried to find a middle ground by forcing a left-to-right flow with the ampersand, but we had to clutter the code with variables again.
Yep.
And finally, we pulled in a specialized external tool to make the code read like a fluid, perfectly intuitive sentence.
It's a brilliant microcosm of the daily decisions you have to make when designing anything complex, really.
Oh, definitely.
Whether you are building software, structuring a massive spreadsheet, or even just outlining a presentation for your department, you have to ask yourself who you are building for. Are you optimizing for how fast you can construct it in the moment? Or are you taking on the harder work up front to build a seamless, frictionless experience for the person who has to decode it later? Empathy for the reader is honestly the hardest feature to implement.
It really is. And if you've ever tried to decipher someone else's nested spreadsheet formulas, you know exactly how valuable that empathy is.
Oh, absolutely.
I do want to leave you with one final thought to ponder, though.
Okay.
To achieve this perfect, frictionless state of readability at the end of the post, Aang had to rely on a completely external tool. It wasn't native to the environment.
Right.
And it raises a fascinating paradox about the tools we use every single day. Does our relentless pursuit of making things look perfectly simple and intuitive on the surface actually force us to make the underlying structures vastly more complex and reliant on outside dependencies?
That is a great question.
When we demand that our interfaces feel effortless, are we just hiding a massive, tangled instruction manual inside a heavier box?
It's the illusion of simplicity. The smoother the surface, the more complex the machinery underneath has to be to maintain it.
Keep that in mind the next time you marvel at how simple and elegant a system appears to be. Thanks for joining us on this deep dive into Aang's refactoring journey. We'll catch you next time.